I want to thank everybody for joining today. We've got a packed program, so we have Kevin Wise is with us, Brandon Birchmeier and Ron Benscik along with Rob Nugent. Before we get started with Kevin, I'm going to go ahead and open up a quick poll here, just as a little bit of an engagement. Just take 30 seconds or so if you can answer these for us. Give a little time for others to get in. I'm sure we'll have some few people getting in too. If you do have any questions, down at the bottom, you should see a toolbar in your interface. There's the chat window, which is the little kind of text icon, or there's the question mark next to it. Feel free to add any questions to either of those, and we'll be moderating those. So, all right, I'm going to go ahead and I'm going to close the poll here real quick. Okay, thank you very much. And with that, I'm going to hand it over to Kevin.
All right. Well, thank you, Shane. Can you hear me okay?
Good.
All right. I think my video is a little lagged, so I'm going to try not to move too much. But hey, I'm Kevin Wise. I'm the commercial leader for the iMFLUX business at RJG, and we're thrilled to have everybody today. Really, there's some great names on here, a lot of familiar ones, a lot of new ones as well. So, you know, we have a couple of objectives. One is we want to kind of update everyone on the next chapter of iMFLUX with RJG. And we're very excited to be a part of that, and looking forward to talking about that a little bit more today. The other one is, you know, if you have an interest in learning more, we want to direct you to the RJG website where you can fill out a form and get more information, and we can maybe answer more direct questions that you may have that's relevant to your business through that venue as well. But to start with, what we'd really like to do is bring on Rob Nugent. Rob's the CEO of RJG, and just to have a couple of questions for Rob that may get this session off to a good start. So, Rob, are you there?
I am here. Can you hear me okay?
All right. Yeah, I can hear you.
Woohoo.
Glad we got a big group on here, Rob. So let me just kick off maybe with a couple of questions. First, you know, from RJG's perspective, what made the iMFLUX technology so compelling that you chose to acquire the exclusive rights? And, you know, what problem were you really trying to solve for RJG customers?
Yeah, great question, and thanks everybody for attending. I'm very excited about this next chapter and where the iMFLUX technology, you know, could take the industry. So from our perspective, you know, the patented low constant pressure molding process really aligns clearly with our mission of providing to the industry advanced process control options, driving efficiency, driving part quality, just driving better molder performance. It's kind of the reason why RJG exists, and that's right in line with what iMFLUX is really all about too. We're both companies are rooted in a data-driven, science-based molding. We don't believe in, you know, doing control from the plastics point of view, and really using that to drive, like I said, great molder performance. I think it's a winning combination of the iMFLUX adaptive processing technology, along with RJG's deep processing knowledge, our strong portfolio of cavity pressure sensors, our training and consulting capabilities, and our data analytics that many of you, our clients, are using in order to be able to drive, you know, substantially better performance. And lastly, I would say with you know, iMFLUX has probably the largest IP portfolio in the industry focused on autonomous molding. And so I think that the combination of the RJG technology and the iMFLUX technology, along with the RJG and iMFLUX team's deep processing knowledge really is a great platform to build on to drive industry-wide autonomous molding practice. Not just taking autonomous molding from small niche applications where they might work well to having a platform that can broadly drive better performance at reduced costs. And that gets to the problems we're trying to solve. The problems we're trying to solve are the similar problems that I think each and every one of you grapple with every single day. The first problem we're trying to solve is, reducing costs. With the iMFLUX technology, the ability to drive a lower material spend by using wider spec materials that have greater variability, using higher percentage regrind so that you can use up all of that scrap and maybe even get some scrap material from other sources that are much less expensive. So the first off is so much of our costs come from the material side, and material costs are going up double digits in some areas year over year, and being able to drive that down is a significant advantage of the iMFLUX technology. Not only reduction in the cost of the materials, but reducing material usage due to a reduction of not having to overfill or overpack the materials because of the low constant pressure technology. And then lastly, around the cost side, you just have a need for lower machine tonnage. That's less energy usage. That's less maintenance that you have to do on your machine and on your mold. And just so cost is a number one piece that we really think the combination of RJG and iMFLUX together can really drive out. The second and probably the most visible problem that we're trying to solve is the skills gap. The ability to have a kind of a set it and forget it kind of a mentality, and having adaptive technology that adapts to the normal variation that occurs during a normal molding process. This normal variation is not whether your machine is totally broken down, but it's normal variation that comes from temperature variation, humidity variation, material variation, just normal shot to shot difference that just is a part of the injection molding world. Like that's what this technology is designed to adapt to, right? And make adjustments for without having to call in process engineers periodically and make adjustments to the machine. The adaptive process technology takes care of that. The third would be, higher performance, right? The ability to drive faster cycle times, ability to drive lower scrap, higher OEE, higher uptime, just the ability to have increased capacity without adding new machinery is just something that this technology just begs to go out and find applications where that could come true. And then the last area that we hear a lot of clients saying that they have problems with is around the ability to drive a sustainability initiative without having to spend a lot more money in the process. In other words, how do you run recycled materials that aren't so compounded that they have to act like virgin materials? How do you use, again, more regrind? How do you use less expensive or less processed recycled materials in order to be able to still produce a good quality part? Well, that adaptive technology of iMFLUX has the ability to do that. Now, many of these can be accomplished with decoupled molding as well. A lot of our clients use D3 processes, and those D3 process, the VDP transfer, allows for a lot of these same sort of benefits. The key is by combining both of these, now you don't have to choose a decoupled or a constant low pressure. You could actually choose which one is going to work for you depending on what you're looking for and what are your business goals. And now you've got a partner of RJG and iMFLUX working together that can be an unbiased guide, provide you unbiased guidelines and consulting to help you understand what is the right processing methodology that will actually drive your business goals. And so it's that combination that I think is going to be that broad platform. So no longer are we talking about niche applications where you solve for one unique part or one unique material or one unique machine, but a platform by which you can have multiple options you could choose from, and a partner that can help guide you to the ones that are going to be best suited, to fit your needs. So those are the major reasons why we thought it was very compelling to work very closely and to work to get this technology and get access to some of the intellectual property.
That's good, Rob. Thanks. I think couple of things you mentioned there might be some new words to the industry. One is autonomous molding. And you've talked about publicly, and you mentioned here that path to autonomous molding and the innovation going on that RJG is pursuing. Talk a little bit about the short-term benefits and access that customers have, and also what to expect in the long term as it relates to that innovation.
Yeah, great question. And, I tell you what, the term autonomous molding is a very broad term. It can mean a lot of different things. And so when I'm using that term, at least in the short term, the things that we are focusing on is what I would call like autonomous process adjustment, things that are happening within the cycle. How do we make adjustments to normalize the normal variation that happens during the normal course of the molding operation, and making adjustments to that process in order to be able to make sure that you make a good part every single time within specification that's at the absolute lowest cost. And so in the short term, that is our focus. The good news, as I mentioned before, is the iMFLUX came with the broadest autonomous molding intellectual property in the whole industry. And the great news is, as we looked at it, we discovered that a lot of that technology, a lot of those patents, not only apply to low constant pressure, but also could be applied to what you'd consider to be legacy decoupled molding methodologies. And so what you'll see from us is we'll start to invest in the already strong technology platforms that already exist out there in the market today, the Copilot and Hub system from the classic RGG, the iMFLUX black box that many of you have seen or maybe worked with in the past. We're going to continue to make investments into those platforms, but we're going to start to utilize capabilities of the iMFLUX system in the decoupled arena and potentially vice versa, and try to cross-pollinate those capabilities so that we could drive a better user experience, broader application benefits, and how do we use that to really drive out ways that you can again choose what methodology you're looking for. In the long term. And then in addition to that, you'll see us embedding the iMFLUX low constant pressure process into the already strong and industry-leading training and consulting capabilities that you've come to know at RJG. In the long term, we're investing heavily in actually driving those technologies together so we can provide a truly differentiated autonomous, quote, set it and forget it process adjustment, so that you can take the intellectual property of that exists and we're going to develop for the future, but add that into a decoupled or to a low constant pressure, and then pick the best ways to actually control those processes in order for us to be able to have a set it and forget it, have a autonomous process adjustment or autonomous molding strategy that could be broadly applied, simply implemented, and that you could use without having any hesitation. And so that's what we're doing long term, is really trying to figure out how do we drive both of these technologies together to become a much broader platform for the industry.
And we're going to get in to a little bit of the technology. We're also going to talk about, in the very short term, if you want to get started with utilizing this technology in the current iMFLUX retrofit product, how we start with that as well. And, so I really appreciate you kind of outlining what that longer term commitment is to the industry, and how hopefully the customers of RJG and iMFLUX can count on that going forward. And so we're really proud to be a part of RJG now. And Rob, thanks for that insight. Anything else you want to add?
No, just really appreciate everybody attending. We're excited about answering whatever questions you may have during this call, and we're actually absolutely excited about coming on site and doing an evaluation about what is the right kind of technologies you could deploy in order to be able to make sure that you're meeting your company's goals.
Good. Well, thanks, Rob. I will say I know I had to turn my video off. It was lagging quite a bit, so I am here behind the initials. But the way we're going to kind of go forward from here is I'm going to talk just a couple of minutes about a few ways that we often see this kind of molding yield some value. And then we're going to turn it over to Brandon, who's going to talk about how that value shows up in your molding processes and really talk through the technology. And then after Brandon goes, I'll be back with you to talk with Ron Benscik, who's our operations leader with iMFLUX, how to get started and what are the steps that need to be taken so that you can understand, if you're interested, what's required. So with that, I'm just going to, I'm going to share a quick file here. Hopefully it's, maybe Shane, can you confirm I got a screen up?
Do not see it right now, Ron. Or Kevin,
Okay.
sorry.
All right. Let's see.
Here it comes.
Here it comes.
There we go.
All right. So is that visible now?
Yes, sir. Looks
Okay.
good.
So just a few quick points to set the stage for Brandon's technology discussion. When you operate with iMFLUX, you're utilizing lower injection pressure, and that injection pressure is also constantly managed. And what that really means is you don't have a traditional transfer position. You get to enjoy lower pressures in all of your molding operations. We typically see 30 to 50% lower pressure. That translates into having the availability using smaller machines and lower capital. And then a lot of times the first conversation we have with customers that have existing processes they're having difficulty with is they're having a difficult time filling cavities with the tonnage of the machine they have or with the mold design that they have. And often iMFLUX can step in early on and help solve that problem. So underneath the lower injection pressure, those are some of the bullet points I want you to think about as you're listening to Brandon discuss how the technology works. The other thing that offers, once you have that lower constant pressure, you have increased process flexibility. And Brandon will talk about how in an injection process with iMFLUX, velocity is variable and pressure is fixed. And that opens up a lot of opportunities for creating value. It often leads to much lower scrap, often 50% lower scrap than we see with a process that has to manage through a complicated transfer position. And you can imagine how defects can occur there, and we'll talk about that a little bit more. Rob mentioned, a difficulty with managing labor. Well, with a constant pressure process, you've got less operator touches. You're not requiring the management of that machine like you are with a conventional process. That leads to less unplanned downtime, and that yields obviously higher OEE or throughput. And then the other thing with the process flexibility is that we solve lot-to-lot variation problems and any problems that arise when you're trying to process any kind of high variability material. So any kind of recycle demands that your customers are asking for or your management's asking for that are causing a lot more downtime and scrap, iMFLUX and this kind of processing can really help address that. Then on the bottom of this this framework are a couple of key points too. One is sustainability benefits and energy efficiency. And we had Underwriter Laboratories come out and do some certification for us. And through lots of process and testing through that organization, we've got 15% energy savings opportunities, along with lots of part weight reduction opportunities as well. UL was offering up to 4% part weight reduction, and Brandon will talk about how that's possible with the way our process runs. And then something that's not utilized a lot, if you've seen us at shows, you've seen us demonstrate this, but one of the things that iMFLUX really shines at that isn't fully leveraged yet is managing significant MFI material shifts. This occurs in recycle streams and in situations where maybe you've got to change suppliers and you've got maybe the same spec, but for some reason it's just running differently. The influx process can manage through that without updated touches. And then you can see the range that Underwriter Laboratories was able to certify to. The other part really then is, this energy efficiency, and Brandon, I think, will touch on that as well. So if you're looking for the next step, maybe you went from hydraulic to electric machines, you've got another whole range of options available with an influx process on the energy side as well. So those are some of the key areas. And then just kind of to summarize, I bucket them this way when we talk to customers. Between the cycle time reduction and less touches and less downtime, you're really looking at 20% operational efficiency improvements. We see this quite a bit. A lot of people start with wanting cycle time reduction, but see a lot of their benefit with less downtime. We have customers that report, we haven't touched the machine in weeks, whereas we used to have to touch it multiple times a shift. And that's part of that autonomous characteristic that Rob was talking about as well. We also see a lot of scrap reduction, which is really driven by better quality. Less sinks, voids, other indications like tiger striping and shadowing and ghosting and other things. With the way we process, which Brandon will talk about, we see almost consistently across the board significant scrap reductions. And then the 10 to 15% energy savings, but also thin walling opportunities and lightweighting opportunities, as well as going ahead and grabbing those recycle streams that maybe either your management is pushing or your sales guys that are out selling business are bringing to you, that are very difficult to hit today. So this is just intended to be a quick summary of some of the value opportunities that we think are available. And I wanted to set that stage before handing it off to Brandon so that you could have that context as he's walking through the next step. So with that, Brandon, are you ready to roll?
I think so. Just pop
okay.
in. So should pop up on your screen here shortly.
Yep.
Good. Everyone seeing that now? All right. Okay. First, super excited to be here today. For those of you that know me, not only is it an honor to talk about influx, but this is super exciting, and I'm elated to be doing this. So, and this is my favorite thing to talk about. So, what a coincidence. So we'll dive right in. I'm going to try to do this in 15 minutes, which, again, for those of you who know me, that might be hard to pull off, but I'll do my best. So here we go. Let's talk about influx. All right, so let's first start off by talking about what the influx system is, okay? You get three main components to your influx system. The first is a nozzle pressure sensor, and that's a sensor that gets installed between the end cap of your barrel and the nozzle on the machine. So when I talk about pressure throughout the rest of this presentation, this will be talking about plastic pressure measured right at the nozzle, and that's how that pressure is controlled. And the control happens through a box, so this little black box that gets installed on your machine. And what that controller does is controlling the voltage to your proportional valve or your on your electric machine to your load cell driving injection. So that'll dictate how much velocity. Essentially, the voltage means velocity, how fast that screw travels during the injection phase. And then there's an independent user interface as well, allowing you to set up your process and your parameters, which we'll take a look at in this presentation. So the way influx works is we bring in some inputs. Those inputs being, like I mentioned, a nozzle pressure sensor that's installed between the end cap of the barrel and the nozzle of the machine, measuring true plastic pressure. We're also bringing information from the machine side, so like hydraulic pressure, if it's a hydraulic machine, obviously. Screw position, a run input, knowing when injection happens, right? That's when the influx system takes over control. And we can also bring in information from a cavity pressure sensor, right? So RJG, being a supplier of such sensors, we can bring that information into the system as well and make that system react to. And I'll talk about those advantages and how those are utilized in the system. And there is one output, just like the title says. The system's doing one thing. It is sending voltage to your screw and telling your screw how fast to go. That voltage is telling that proportional valve how much to open or close, which is oil. More or less oil tells that screw to move faster or slower. So it's real-time control of screw velocity to maintain a pressure set point. So let's first talk about the decoupled molding process, right? The process that is, by far the industry standard. This is how I was taught to mold. This is how you'll learn how to mold if you go to the initial master molder training classes as well. And what you have is a multi-phase approach, right? You have a velocity controlled fill phase, right? At 95% full, right? Was how we're taught, right? You're going to maintain typically a high speed injection speed, use that rheology, take advantage of that shear thinning of the material, which is typically a fast, high velocity. We transfer that 95% into our pressure phase, right, until we achieve gate seal. So we have our pack and hold phase, right? So it's a decoupled approach. We have a fill phase and a pack and hold phase. One is velocity controlled and another is pressure controlled. So influx changes this in that there is only one phase, and that's only pressure. So we're at no point in the influx process do you actually preordain the screw movements. And what I mean by that is, right, today your injection molding machine is really good at listening to you as an operator, but it's pretty agnostic to the mold itself. You tell the screw to inject at 4 inches a second, by golly, that's what it's going to do. It's going to try to inject at 4 inches a second. Those are preordained movements that you as a processor tell your molding machine to achieve, right, through process development and whatnot. Well, influx, where I get excited about the influx process is the mold is always driving the decision around screw movement, meaning it's always an important part of the equation. The mold is really making all your decisions. What I mean by that is that geometry in that mold and those pressure losses or change in nominal wall thickness. And we can account for those in real time because of pressure. Nothing's preordained. This screw movement, this velocity I achieve in this process becomes naturally due to the constant pressure process. So let's talk about what you're seeing here. This green line right here is the constant pressure process, right? That is that plastic pressure. And what's unique about this is the velocity curve you get to achieve that. So what happens is as I'm coming up to that pressure set point is we are stepping on the gas. We want to go pretty fast, right? We want to take advantage of the rheology of the material, the shear thinning properties, and we still want to shear that material. Rather than shearing it from, start of injection to that transfer point at say 90-95%, that's only happening for a very short portion of the part, about the first 5 or 10% of the part. Are we really shearing that material for high injection speeds? Then once pressure is achieved and maintained, you get this deceleration that happens in the screw velocity. So two things are happening at once at that point in time. I am continuing to move the screw forward, but as it moves forward, it goes slower and slower and slower. It allows us to densify that part while the flow continues to move forward. So rather than having a independent fill phase and a pack phase to kind of fix everything I screwed up during fill, it's this packing that part out while it fills. We're taking, if you think about the efficiency of the screw movement here, we're achieving two things at once, moving the plastic flow front forward, but also densifying it while we do. And also running with constant pressure has some really unique advantages we'll talk about as well. One thing that I should point out here, traditional molders, right? If you look at this, you may think to yourself, well, why would you run a pressure limited process? That sounds crazy. You don't do that. 100% agree. You don't do that. What's important about is how a molding machine reacts to a constant pressure kind of pressure limited scenario and what happens versus when you're actually controlling via pressure. So when you are reaching pressure limitations in your process, you effectively lose control of your screw. You may tell your screw to travel 3 inches a second. If it's peaked out at pressure, it can't achieve that anymore. So you kind of are just at the, whatever that pressure can achieve is what happens. And you may see that that will kind of rise and jump up against that upper limit. Well, this is why the iMFLUX system has its own tuning parameters as well. We will tune your machine to get this sort of response we want out of it. Again, that's a lever you don't traditionally have. You're typically locked out of your PID tuning parameters inside your machine. That's something that we open up to you in the process to get the kind of response we're looking for, this shape and that velocity curve, while we're controlling pressure. So it is a pure pressure control. And again, for those of you who've been in the industry for a very, very long time, you may be thinking about boost machines, right? So how did we control injection molding before velocity existed? Actually, it was a similar fashion. We used to do boost pressure. You used to have your boost pressure and your hold pressure. A similar scenario, but we didn't have the sensing technology, right? So everything was based off of hydraulic pressure, which is not a great proxy for plastic pressure, especially when things are moving, right? You have a non-Newtonian polymer and a Newtonian hydraulic fluid. Those things don't coincide extremely well, especially during fill. So much better sensing technology, right? We're getting at the plastic, which is what we care most about, and we're letting the mold make lots of decisions for us in our process. And I'll elaborate. So again, much lower pressure process, like Kevin mentioned, we're seeing typically 30 to 50% reduction in peak pressure. This is typically what you're fighting against if you think about your clamp tonnage force. And we do fill the part slower, right? So 95% full on this part is much farther in the process. Overall, this part does take longer to fill than it would traditionally. However, we eliminate this independent pack and hold phase. So if you think about injection forward time, fill, pack, and hold all summarized, the iMFLUX process is actually typically less in injection forward time, even though it takes longer to fill. So let's look at a couple of graphs here real quick. And this is what a graph would look like on the iMFLUX controller. So a couple of things to point out. Again, this is our typical decoupled molding approach. We have a high velocity controlled in fill phase. As we maintain speed in this line here, pressure, this blue line, continues to increase as velocity is maintained. And here we can see our screw position moving as well. And then, we go into transfer, right? We need to transfer into that hold phase. And unfortunately, that can be a pretty violent event sometimes. And what often happens is you get things like screw bounce, right? You're generally speaking, trying to get to a pressure, maybe 50% of peak pressure during fill. When you do that and you go from a velocity control to a pressure control, that switch over point in your process allows things like screw bounce and erratic movements to happen in the process. Another thing I want to point out here in this process is this has a cavity pressure sensor in it. This has an end of fill sensor in this application. And what this end of fill sensor is exhibiting is something that's kind of commonplace in our traditional decoupled approach, and that is the skinning of the polymer. Right, I'm skinning the polymer layer on the steel here, but I'm not pressurizing. There's nothing behind it. So I'm getting a little bit of pressure, but it doesn't densify and pressurize until I'm well into my hold phase here. So this just shows that skinning effect, right? We skin that layer and then it densifies after transfer. And you can see that in this cavity pressure sensor here. Keep that in mind as we look at an iMFLUX example. So now that same part with iMFLUX. So my green line is plastic pressure. This is what I'm trying to achieve. Here is my screw velocity. Notice it's never stable. It's always moving. It's always adjusting. And that's what I'm looking for. This velocity is dictated by the geometry in the tool in this shape. Again, I'm getting that high speed up front, but it's slowing down as the flow front continues to progress. That allows us to pack the part while we fill. And you can see that in the end of fill sensor right here. Notice as soon as the plastic gets in the sensor, it densifies right after the fact. That's what we're looking for. I don't want to have to, short shots that are packed out parts. I don't need to fix those things and pack and hold. They don't exist in the first place, which is kind of the goal of the process. So one thing I wanted to elaborate on, and especially as we talk about the RJG and iMFLUX, partnership, and why I'm, as you can imagine, super excited to be here, is how cavity pressure makes this process so much more alive and actually improves it. The genius of Rod Grollo and the first cavity pressure sensors and using that to transfer into pack and hold was, obviously industry changing. What's neat about iMFLUX and how we use cavity pressure is the entire topography of that cavity pressure curve is now influencing the process. If you've done, decoupled molding or decoupled 3 molding, you're using a single point on a curve to dictate transfer. Say I want 1,000 psi at my pressure sensor, and that'll transfer me into my hold phase. Well, iMFLUX uses something called PFA, or pressure factor adjust, which means is as we realize cavity pressure, and typically at an end of fill sensor, we will follow that topography in typically a mirrored fashion. So what I mean by that is a PFA of -1, which I have highlighted here. As pressure increases, a -1 PFA means it's a 1-to-1 response. So for every PSI of cavity pressure I realize, I am mirroring my pressure response in the opposite direction. So 1-to-1. If my PFA is a -2, it's a 2-to-1 response. If it's 0.5, it's a half of a PSI response. So you can see this is a way to transition into those lower, like I would say, hold phases, but very, very gradually. We're utilizing that topography of the curve to start breaking the process, rather than that hard transition, right, that happens at transfer. And something that decoupled 3 addresses through velocity pack, you also achieve here, right? It's a more gradual, less, I would say, erratic transition. And this is all pressure based, right? So we're not even going from a velocity to a pressure control. I'm not asking my machine to do anything necessarily differently at this. I'm able to progress into a lower pressure if I need it, say at hold, very, very smoothly. And I'm using that entire topography, the eternity of that curve in this response, which if you think about, I want to utilize it, I want to get as much value of my cavity pressure curve as possible. This is one way you're achieving that through PFA, which I think makes, a lot of sense why this technology is continuing to advance under the RJG umbrella. I mentioned packs as it fills. Here's a real life example of that. And if you have little kids, these are Pamper baby wipes. Again, this technology was developed within P&G, so you're going to see some P&G examples here. But this just shows you what does a short shot look like typically. Usually you have a lot of orange peel, a lot of sink, right? The reason we need to have a pack and hold phase is we need to repair a lot of this, right? So it looks nice. Well, if that part packs as it fills, I don't need to go back and fix it. I don't have these defects that I need to fix during the pack and hold phase if I don't let them exist in the first place. We'll play some quick videos here for you. So again, if we compare a traditional high rheology, high speed, right, we want to thin that material process, and we get this skinning effect of the polymer versus a thicker frozen fraction. What this is trying to highlight is you have that much thicker frozen fraction in the iMFLUX process, much less fountain flow through the center, but also it helps things like gate seal happen very, very quickly if you think about the cross section of your gate during fill in the shear that's generated. So here we go again, another P&G part. What I want to highlight on this is a living hinge part and an advantage we have because of the significant geometry changes that happen in a part and how we're able to recognize and react to those changes, right? Like I mentioned before, geometry dictates velocity. I want this shape of this part to dictate what's happening in my machine. And I get that through the constant pressure molding process. And you can see that in this velocity curve. Again, as I try to achieve my set point pressure, I'm going to create some velocity as I do so. However, as soon as I hit that living hinge section, right, what happens is that creates resistance in my part. And now I'm going to react to that resistance. It'll slow down, and you see this dip in speed here as it hits that living hinge. As it exits through the hinge and it's easy to fill again, it'll speed back up. This topography of velocity is directly impacted by this geometry of this part. Your mold is controlling your machine, which is that's a big deal in our world, because we want to make real-time smart decisions about what's happening in our process. The more the mold influences that process, I think the better your chances of being successful in those endeavors. And the other thing that's important to point out is this curvature in your speed, you can't program a molding machine to do that. You have step functions traditionally in your molding machine. I can go 1 inch a second or 5 inches a second or 3 inches a second, but I can't control acceleration and deceleration. That's something you get out of the iMFLUX processes, the ability to have curvature and velocity, which means much smoother movements of your screw. Again, we're not making erratic changes. Everything is very smooth in the iMFLUX process. The next advantage we get out of the process is something called auto viscosity adjust. So if any of you are familiar with how your material gets tested, your MFI test, that is a constant pressure process. You put some weight in a little vial, and that weight squeezes some plastic out as it's heated up. And that's where your MFI comes from, your melt flow index. It's a constant pressure process. When we mold with constant pressure, we're essentially turning your barrel into a giant rheometer. And what we do is we try to understand fill time changes, and we will utilize cavity pressure to do just that. So what auto viscosity adjust is looking for is, do I need to change my driving pressure because my fill time changed? Traditionally, you control fill time because you're saying inject from shot size to transfer at this given rate, and it's an extremely consistent number, right? You are determining fill time based on your set points. Well, when you mold with pressure, you don't. Your fill time is kind of an output of that process, but we want to maintain that output. So what will happen is that pressure profile will, that pressure profile will increase or decrease to maintain that same fill time. And you'll see this in this example here. I'm using cavity pressure feedback, and the process in this example actually reduced itself. It's trying to maintain that fill time. So if you are running high recycle, post-consumer regrind, what we're doing is we're getting a read on every shot of how easy or how hard that mold was to fill, and making an adjustment to your pressure to close that loop. Right, we're always trying to maintain that same fill time. We do it by controlling pressure up or down. Kevin mentioned less energy consumption. Where does that come from? Well, a lot of it comes from when we reduce peak injection pressure, I can reduce clamp tonnage. So I get those savings. I get the savings from the less injection energy needed because of those peak injection pressures aren't being achieved anymore. I've eliminated the pack and hold phase, so the inject forward time. Also, we're typically reducing some cooling time. We'll talk real quickly about how we can improve things like warp. So about 20% less energy in this example. Like Kevin mentioned, we have that from UL at 15% with the testing we did with them. So we can do some pretty crazy things with this process as well. If any of you ever seen me at a trade show running iMFLUX, you might have seen me making this part right here that you see. This is the mini runner, a part and mold we made on purpose to kind of demonstrate really to the nth degree how geometry drives velocity and how this part is controlling your molding machine. So in this part, as you can imagine, this sprue fills pretty dang easy until it hits this 30 thou runner system that happens to be 3 inches long that I have in front of me here. As you can imagine, if I'm molding this at if I'm telling my molding machine inject at 2 inches a second or 3 inches a second, as soon as it sees this transition in geometry, it gets a huge pressure spike and it wants to flash. Your molding machine doesn't know any better, right? You would need to do some pretty wild profiling to probably make this work in a conventional process. This happens automatically when you're molding with pressure. These thick sections fill fast and these thin sections fill slow. So as soon as it sees this choke point in the process, it can slow way down as it maintains pressure as it goes through the runner system and then into this subgate and then actually packs that part out. So as long as it doesn't hesitate, it'll continue to flow. And this geometry and your wild geometries you may have out there is really controlling your molding machine in real time with this process. Talk about reduced stress. A lot of that comes from the elimination of the pack and hold phase, right? So we use pack and hold because we need to compensate for all the pressure loss that we achieved during the fill phase, right? We now need to pack all that, densify all the internals out of the part. Well, unfortunately, when we do so, we create stress concentrations near our gate locations. So in this part here that's gated at the bottom, this is polycarbonate. During our pack and hold phase, we are, a lot of that is concentrated near those gate locations as we're waiting for that gate to seal, right? It's not like we're really pushing plastic out here. We're localizing all of that pack and hold near those gate locations. Well, if I'm packing that part out while I'm filling, I don't need to come in after the fact and pack that part out. So those stress locations are much minimalized in this scenario. That gate, I don't need to stand on it to achieve gate seal anymore because I'm starting to slow down during my injection molding process. And those pressures are so much less. This part is going to be much less prone to warp. So that's where things like cooling time savings can be achieved as well. Balance of fill, high cavity part, right? As pressure continues to increase in the system, those first cavities to fill see more pressure than the last cavities to fill, right? As that pressure continues to increase in the system. So those first cavities to fill, much higher pressure than the last cavities to fill. That's why balance is so important to our traditional decoupled molding approach, right? Because we know their pressure continues to increase in the system. Well, when you mold with constant pressure, that requirement isn't nearly as critical. We can live with quite a bit of imbalance and normalize and bring the distribution across multiple cavities much closer together because pressure is maintained constant. That first cavity to fill sees just as much pressure as the last cavity to fill because I am maintaining pressure during the process. So much narrowing of dimensions, part weights across high cavity parts. The last thing I'll leave you with is sequential valve gate parts. Big automotive parts are near and dear to my heart if you know anything about my history. And one of the neat things about iMFLUX is how it handles sequential valve gates. And what I mean by that is there's now harmony in the process. So typically as gates are sequenced, so gate 1 here, 2, 3, 4, and 5, I'm maintaining pressure. And I'm getting variation in my fill velocity. It's compensated to changes in gate sequencing in real time. There's harmony between your injection molding machine screw moving forward and those gate sequencing. Conventionally, your traditional molding, you're telling your screw inject at a constant rate. And as those gates sequence, you get massive pressure swings in these parts and beat up party lines, to be completely honest with you. So what's neat is as those gates sequence now is your molding machine is reacting to those sequences, where before it's not. There's two independent systems trying to achieve the same thing, but controlling independently of one another. And here's a great, real life example of that. Here is a mold with, I believe, 9 valve gates. And you can see as those valve gates open and close, how that pressure swings across that part. With constant pressure, you can see how it's just maintained. So all of you tooling folks out there, you can imagine what that does to your party line over time, right? These big molds. And how it's really detrimental to your process, right? You're probably having to utilize more tonnage than you need to, which hurts things like venting, right? So we always want to optimize the process. This is a great way to do that. That is all I have for you. I probably went over my time. I apologize. Anyway, great to share that with everyone. I'm hoping and looking forward to hearing from many of you again in the near future. Thank you.
All right. Well, thank you, Brandon. It's always the one thing that always shines through is your enthusiasm for molding, and it's a bit infectious. So I appreciate that for sure. What I'd like to do now, and just to give everyone a heads up, there'll be an opportunity with a link if you want more information at the end of this session. We can reach out directly. But we wanted to switch gears a little bit and try to address the very short-term question is, hey, if I want to do iMFLUX, what's the first step? And so who we have now is Ron Benscik. Ron is our kind of integration and operations leader for iMFLUX. And he's been at this for 10 years. He's probably one of the world's best integrators into injection molding machines. And I'm going to run through a couple of questions with Ron here on, under that umbrella of, hey, how do I get started? So Ron, welcome in here. Can you hear me okay?
Yes, thank you.
All right, good. So, hey, Ron, when, if a customer calls, we've talked, they've decided, yeah, I want to go forward. What's the first thing you're going to need from them to start that assessment integration process?
Well, generally, the first thing we need to know is, do we have an interface with the particular machine that they have of interest? So basically what I'm going to do is I'm going to ask for the nameplate, because that gives me pretty much of the information that I need to know. And it'll give me a 90% idea of if we have an iMFLUX interface with this machine. And there's workarounds to this. So, but we start with the existing platforms. We have platforms with 22 different OEMs on 65 different platforms of machines. So we're pretty versatile when it comes to that. But that's the first thing we ask for.
Gotcha. So let's say we've got an interface. What's next? What's the next thing that we're going to have to walk a customer through to get them set up for success?
So depending on the order you want to do this in, we'll get a quote out to you, obviously. We'll work with the OEM. A lot of times a customer will have a good contact with their salesperson and they can go straight to the OEM. And in the OEMs, once I say that we have an interface with this, they'll be familiar with an iMFLUX interface. And I'll tell you which type of interface we're asking for. So they'll go to the OEM and we can also request it for you. The other thing we're going to need to get into is we replace the nozzle body on the machine with an exact duplicate of the nozzle body, except it'll take a penetration for a melt pressure sensor, for that sensor at the front of the nozzle. So what we'll do is you can use your existing heater band on this nozzle body. Everything's a replacement. So I'll send you information for gathering the measurements for the nozzle body. If you have an existing drawing, that's fine. Or we have a sheet that you can write down multiple measurements on, and we can manufacture the nozzle body from that. We'll draw a drawing up and then we'll get it back to you for an approval before we place it in the manufacturing queue. Also on the pre-engineering document, we'll be asking for maybe some pictures of the IMM, pictures of the nozzle area, things like that for clearances. We'll be sending you documentation for clearances, things just to make sure that the melt pressure sensor clears. Some machines are small and they have small tunnels. We'll look into all that to make sure that everything's clear before we manufacture the nozzle body.
Got it. And then what are lead time expectations for a customer?
So the lead time for us, it's mostly the nozzle body itself. It's about 7 weeks for the iMFLUX side lead time. Once we have a PO in hand and we have the nozzle body approval from the customer, just figure 7 weeks.
Got it. And then talk to me a little bit about what installation looks like when we get to that 7 week period and we show up at a customer site. How does that work?
So prior to this, we'll be shipping the kit and we'll get with the customer. Sometimes the customer will want it early. Sometimes they want it a few days before the integration. So we'll have someone show up on site. We ask that the OEM do their part of the install at the same time. This alleviates a lot of problems. If there's any questions, if there's any issues during the startup or handover. So the OEM and our technician will do the install simultaneously. So this way it allows for efficient use of the customer time and the minimum downtime on the IMM. So we'll be doing it simultaneously, then we'll work together for the handover. But you're looking at probably 2 to 3 days, depending on the machine size, for the installation and the startup and handover. But also during that time, once we get the handover complete, I take that back. I'm sorry. During the installation, what we'll have is 8 hours usually during a day shift. So just so you know, you can run the machine afternoon shift and midnight shift. Us nor the OEM does anything to the machine that doesn't allow you to run it on the off shifts.
So essentially we're coming in, we got about an 8 hour shift. We're going to need that machine, and customer could be back running conventionally, at the end of that shift.
For the next 2 shifts, if that's necessary. That's not a problem at all. Okay.
And then maybe talk a little bit about how service and training works. If I need help, who do I call?
So what we're trying to do is get this set up with all customers, because generally they've been calling directly or emailing. So what we'd like to do is go through, there's a RJG email, support@rjginc.com. That will immediately put a ticket into the system. This way we can keep track of it. It's better for the customer also. Then this will come over to me and we'll decide who it needs to go to for support. But we have several options for support. We do have some remote options. So we can support customers remotely. And then if necessary, we can schedule an on-site service call if that's what it takes.
Okay. And then we also have training options available. We have our site in Cincinnati. We have a machine. We have a training room. We've got a few different trainers that can help customers with training. And that's an important part of becoming transitioning into, becoming adept at this type of processing. So we're there to support you as well. And of course, RJG is beginning to build in influx processing into some of their base training as well. And so between those two things, I think one of the most exciting things is the ability to help processors and ops folks in our customers and molders to become good at this processing. So that's it we've got in terms of how to get started. So, Rob kind of laid out the vision. We talked about value options. Brandon walked us through how it works. Ron walked us through how to get started. This kind of brings us near the end of our scheduled time. So I'm going to hand it over to Shane for kind of how to handle questions and next steps.
Yeah, so just a couple of things. In the chat, I dropped a link. So if you'd like to kind of get more information or have somebody reach out to you, that'll take you to a form, and on the exit of this webinar, you'll be taken to that form as well. Lots of good questions in the Q&A. So thanks for putting those in there. And I see Brandon's been quite active in answering some of those questions. So just a couple of things that have showed up. What kind of machines? The question is, can we install iMFLUX package to any machine? So I don't know, Ron or Kevin, do you have a response to that?
Well, I wouldn't say any machine, but like I said, we have interfaces with 22 different OEMs on 65 different platforms. And even recently, we've come across a machine that we don't have an interface for. And what we do is we go to the OEM and we'll explain it to them. And with the customer's help, a lot of times for a request for that, we can work on a new interface. So that's not out of the question.
And like in the feedback form, if you can get us a picture of a nameplate you've got in mind, we can get you fast feedback on that as well.
Yep, excellent. Just another question. There's a couple of questions about if you install the system, can you go back and forth? The answer to that is absolutely. So if you're not tied into the iMFLUX systems, to that or no. There's another question here about AI. So I'll just read the question verbatim, and Rob's probably the best to answer this one. Has there been any progress in integrating AI into the iMFLUX technology? Dream would be to completely eliminate need for tuning PIDs, adjusting gains for the auto viscosity adjustment technology, and to allow AI to do it autonomously for the user. Has any of that functionality been achieved, or are there plans for this in the pipeline?
Yeah, I think there's all sorts of different ways to look at AI, but AI is certainly a major part of how we think we can take this technology and adapt it to a very broad base of application space. You speak to a specific example that I would completely agree with you. We're working on that right now, and we'll continue to work on that, but that's going to be more in the longer term, not necessarily in the immediate short term from a development standpoint.
Great. Let's see here. We'll continue to answer these if we don't get to them. I think there was a question, how mature is the mold flow simulation for this process? I'm not sure if Brandon or Ron, if you've got any experience with that.
Yeah, I can speak to that. So Moldex 3D has been a great partner of ours and has provided services for simulating the iMFLUX process. I think we even have some of those folks joining this meeting as well. In addition to that, from the mold flow side, Jay Shoemaker used to work for iMFLUX, and he now has his own consulting business. I think it's Hook, Line, and Sinker. But he provides mold flow simulation for the iMFLUX process as well. So yeah, both mold flow and Moldex 3D have experience doing this simulation.
Fantastic. Let's see here. One of the questions here at the end, what determines the pressure set point for an application?
Oh, well, that would require a whole nother presentation. But there is a methodology. So yeah, we didn't talk about like process development. There is a methodology. Like, I mean, first of all, good question, right? Where do your pressure and times come from? How do you determine those? There is a step-by-step kind of approach. We call it LECR, largest empty corner rectangle, which makes no sense at all in this scenario. But there is training. We do show folks how to find your process window, optimize your process, and find those key parameters. It's a whole different methodology, as you can imagine. Too long to cover today. I probably already went too long.
Yeah.
I would
And
just
know
add that what we hear from customers is that feels a little bit like a daunting task when they first take it on. But then what they find is it's easier to teach new people that process development than it is the previous. So there's a little bit of a challenge in transitioning people to that. But for somebody coming in new that you're trying to bring up and teach, it's actually an easier approach.
Great. Well, we are at time. If we didn't get to your question in this comments, we will make sure that we reach out to you and get questions for you answered. We'll have a list of those that we probably didn't get to. There was quite a few. I got 20 in my list here right now, so just running out of time, but we'll make sure that we're following up with you. Once again, I appreciate everybody that has spent their time the last hour with us today. And if you have any questions, please fill out that form in the chat window, and upon exit, I think it'll take you to that form as well. So we look forward to hearing you. And as I mentioned, we'll keep tabs on these questions, and we'll make sure we're getting responses out to you. So thanks again, everybody. Much
this was
appreciated.
recorded. Proper,
Yes,
right?
it
Shane?
was. Yep, it was recorded.
So it'll be available.
That is correct. Yep, and once it gets, we'll get it out to everybody. A link to this. Once it'll take us a few days, but we'll get it out to everybody as well. Thank you.
To everybody.
Thanks, everyone. Bye.